too complex. Let's kick things off. As usual, question, concept, solution. A borehole log was drilled to a depth of 30 meters, extracted and laid on the surface for inspection. The first 5% of length from the surface is soil. Between 19 meters to 23 meters, there is a peculiar finely crushed rock. Wet mud was also encountered between 29 and 29.5 meters. Determine the percent core recovery. Alright, so first things first, let's get a log in here. So this will be our log. Mind you, all I did was rotate this 90 degrees to make things easier for me. So if we assume this is surface at 0 meters and this will be 30 meters, right? So we are told that the first 5% of length from the surface is soil. So let's just assume that this right here is that 5%. So if we say 30 meters times 5%, right? And this gives us 1.5 meters. That's this distance here, right? And then we are also told that between 19 to 23 meters there is a peculiar finely crushed rock. So let's assume that somewhere here we've got 19 meters, and then here we've got 23 meters. To find the length between the two, we're going to say 23 minus 19, which gives us 4. So this is 4 meters. And last but not least, we have wet mud between 29.5 and 29 meters. So let's just assume this is somewhere here and here. It's a very small space. So obviously 29.5 minus 29 gives us 0.5. Now this here is losses, and our losses sum up to 6 meters. So to get the percent core recovery, we're going to say length of core minus losses over the length of core times 100. Okay, so the length is 30 meters minus the losses 6 meters over 30 meters. This is the same as 24 over 30 times 100, and we get about 80%. A 3-meter cubic shaped boulder was observed in a mine excavation. Joint spacing along its dimensions is 45 centimeters, 60 centimeters, and 70 centimeters respectively. Estimate the rock quality designation for this geotechnical environment based on this boulder and comment on your answer. Now let's start by understanding what is this rock quality designation, so otherwise known as RQD. So this is the ratio of the cumulative length of sticks of NX size core more than 100 millimeters in length in a drill run to the total length of the drill run. Now there's a lot going on here, so for us to understand a little bit better, we're going to use a visual aid. So what we can see here on the diagram, this distance from here to here, that is the length of the drill run. Okay, and these little guys here making up this length are the sticks. So 1, 2, 3, 4, 5. Those are the sticks. If we take this one as an example. Now the NX, that is the core drill size. Okay, core drill size. So that is the diameter that we are using, right? So since it's NX, it's about 55 millimeters. This is what is used for dam, tunnel, and rock mass studies. The mathematical representation of RQD would then be RQD is equals to total length of core greater than or equals to 100 millimeters over length of core times 100. The greater than or equals to 100 means that if we go back to the diagram, these sticks that we showed, we will only take the sticks that are equal to or greater than 100 millimeters. If it's anything less than that, it will be ignored in the RQD calculation. In some cases, RQD can be estimated from inspection of exposed rock surfaces by determining the number of unhealed joint planes per cubic meter of rock, which is the case with our question. So we will look at how this works. So RQD, now it's calculated using RQD is going to be equals to 115 minus 3.3 J sub V, where J sub V is the number of joints per cubic meter. So others may call this a volumetric approach towards the RQD. To find J sub V, we are given joint spacing along 3 dimensions, which would look something like this. Okay, now if we put our cubic shaped boulder, we would have something like this. So this will be our X, this will be our Y, this will be our Z. Likewise, X, Y, and Z. So everything here is 3, 3, 3, 3, and 3. Okay, now if we allocate X, Y, and Z to these 3 values that we are given, you should ask yourself, how many joints can I fit in the X dimension, in the Y dimension, and in the Z dimension? Now we need to recall that this is a cubic boulder, so all dimensions will have the length of 3. So starting with X, we'll have 3 divided by 0.45. We've already done the conversion. This gives us, so we can fit about 6 joints. Okay, and we go to Y, so 3 divided by 0.6 gives us 5. Then we go to Z, 3 divided by gives us about 4 joints. To get J sub V, we then say so J sub V is equals to 6 joints over 3 meters plus 5 joints over 3 meters plus 4 joints over 3 meters. This is a common denominator, 3. Just add numerators there, you will get 6 plus 4, 10 plus 5, that's 15, and this divided by that, this gives you 5 joints per cubic meter. So now we can calculate RQD. Substituting into the formula, we get RQD is equals to 115 minus 3.3 times 5, and this gives us 5. We get 98.5%, and we are done.